Okay, so we're going to look at Kinematics Part One. If you're following this live, this is going to take a while because it seems like after each video is done, it takes a while to process before I can start the next one. So let's have a look at this. So we've got Kinematics Part One, which is essentially SUVAT. And the whole of this entire set of questions relies on just constant acceleration. And your clue is there's no t squareds anywhere, okay? So with constant acceleration, we get given all our formulas. So it's just our SUVAT formulas, right? Okay, let's see if we can make this bigger. Oops, a bit bigger. All right. So we've got a particle P moves with acceleration 4 - 5. And at time t equals 0, it moves at velocity -2, 2. And you want to find the velocity at t equals 2. So we know that SUVAT, we've got acceleration is 4I - 5j. At time t equals 0, so that's your initial velocity, is -2I + 2j. And we want to find out when t equals 2. And we're looking for this. So we're going to use v equals u plus at. So we've got -2I + 2j plus 2 lots of 4I - 5j. We clean that up and we get 6I - 8j meters per second. Then it tells us at time t equals 0, P passes through the origin. And at time t equals big T, the particle P passes through the point A. The position vector of A is lambda I - 4.5j. Okay, find the value of T. Okay, so we've got our position vector, so that's a distance. So we've got lambda I - 4.5j. Okay, and we know that's at some point. So instead of t is 2 here, that's at some point big T. Now here is where it's probably easier to write it as a column vector. I prefer always writing vectors as columns, but each their own. Some people don't. But here I definitely think it's easier. So we're going to use S equals ut plus 1/2 at squared. So we're going to get lambda - 4.5 equals -2 big T plus 1/2 4 - 5 big T squared. And if we have a look, we can consider the i's and we can consider the j's separately. So if we take the j's and we make that all equal, so we're going to get -4.5 equals 2t - 5/2 t squared. And then you're going to put everything on one side, plug it into your calculator, and it will tell you that t equals 1.8. Okay, so if you don't know how to use your calculator, have a look at some of the calculator tutorials, but it's menu, equation, and you just plug in your quadratic equation. So now we have lambda equals -2 big T plus 1/2 of 4, which is 2t squared. We can substitute the t in, and we get lambda equals 2.9. So that's a relatively straightforward question. Don't be scared of vectors. Treat it in exactly the same way that you treat everything else. Okay, next one. Right. A radio-controlled model boat is placed on the surface of a large pond. And time t equals 0, it's moving due north. So by due north, we just mean, it's going up. So I don't know, no elephants swim west. No, never ever, I don't know, was it never eat shredded wheat? I'm not sure which one you've ever used, but there are various different options. And so it's due north, which is going up, which in vector world is +j. So we know at time t equals 0, our u is 0.6j. So it's 0i and 0.6j. Relative to O, the position vector is R. At t equals 15, the velocity is 10.5 minus 0.8. Show the acceleration. So SUVAT, we know that U, we've just said, is 0.6j, t is 15, v is 10.5i minus 0.9j. So we've got v equals u plus at, which is going to give us 10.5i minus 0.9j equals 0.6j plus 15a. You're going to rearrange that for a, and you get the answer of 0.7i minus 0.1j. Okay, so that's quite straightforward. So now we want an expression for r. R is just the vector world way of saying rs. So we're like, what do we know? We know u, we know a, and so all we're going to use is s equals ut plus a half at squared. Let me clear that because you can see what the acceleration is above. So our u is 0.6j. So we're going to get 0.6jt plus a half a, which is 0.7i minus 0.1j t squared. And now it says, find the value when the boat is northeast. So these are quite, you've just got to think about it. What's happening when something is northeast? Well, northeast, the line is here. So that's the line, if you like, if it was an xy axis of y equals x. So in vector world, it's when I equals j. So it's when your I components equal your j components. So if I was to write this r as a in column vectors, because like we said, sometimes it's easier to do so, you'll see that r equals 0, 0.6 t plus a half 0.7, 0.1 t squared. And we're saying the I component, which is 0 times t, which is just 0. So a half of 0.7. So a half times 0.7 t squared equals 0.6 t plus a half times 0.1 t squared. You can cancel one of the t's out, rearrange it, and you get t equals 1.5. So that's when the boat is northeast. So this is when the r, when the boat is physically northeast. Now it's telling you, find the value of t when it's moving. Now remember, movement is represented by velocity. So your velocity is v equals u plus at. We know our initial velocity is 0, 0.6. We've got our a, which is 0.7 minus 0.1 t. And now we're saying it's going northeast, so the same thing applies. It's when the I equals the j. So that's what you need to remember. You see northeast, you think I equals j. So you're going to get 0.7 t equals 0.6 minus 0.1 t. And you rearrange that and you get t equals 0.75 seconds. Right, next question. Okay. These are all vectors and these are all look a bit familiar. So they all start to look the same after a while. At time t equals 0, it's moving at time t. Okay, so position vector is essentially our s in SUVAT. So we've got SUVAT, you've got 7i minus 10j, we've got an initial velocity of 2i minus 3j, and we've got t equals 2, and we're trying to find a. So we're going to use s equals ut plus a half at squared. So you're going to have 7 minus 10 equals 2 minus 3 times 2. plus a half a times 2 squared, which is 4. So times 4, that's going to cancel, give you 2. Put everything on one side, and you end up with 2a equals 3 minus 4. So that's going to give you a equals 1.5 minus 2. But we want the magnitude, which means you want to Pythagoras it. So, or find the modulus of it. So that's just going to give you 1.5 squared plus 2 squared, which gives you the 2.5 squared at 2.5 meters per second squared, as required. Oh, that makes sense? So you just used your normal SUVATs, but then you found the magnitude. Okay. And let's just rewrite that up here. So A came out to be 1.5i minus 2j. At the instant when P leaves the point A, the acceleration of P changes. So P now moves with a constant acceleration 4 plus 8.8 meters per second. Now we know where the point A is. So first of all, this is like if you've seen the the pulleys question, we want to find out the V just before anything changes. So we're going to use V equals U plus AT to find the V at A, so at the point A. So we've got our U, which was 2i minus 3j, plus our A, 1.5i minus 2j, times the time it took, so times 2. So we end up with V being 2 plus 3, so 5i minus 7j. So that's our V just before the acceleration changes. So it now becomes my new U. And now I want to find a expression for V in order to then equate them. I've got this northeast again, where we got the i's equal j. So my new V is, my old V becomes my new U, right? Plus V equals U plus A, which we've been given as 4, 8.8. And the bit we don't know is T. But we know it's moving northeast. So I equals J. So if we take the top line, we get 5 plus 4t, and that equals minus 7 plus 8.8t. Nice simple algebra, and we get 2.5 seconds. So northeast, I equals J. That's what you're going to remember. Okay, next question. Oh, that's 5. Oh, here we go, question 4. Right, a particle moves with constant acceleration. T equals 0, it's moving with velocity minus I plus 4j. And at time t equals t, it's moving in the direction. Okay, so it's not telling you, this isn't how it's moving. It's just telling you it's the direction. So it means that the velocity could be any factor of 3i minus 4j. It could be 6i minus 8j. It could be 1.5i minus 2j. It's just some factor of it. So first of all, we're going to find an expression for V. So V equals U plus AT. And you see how all of these start to look the same after a while. So we've got minus 1, 4, plus A, which is 2 minus 3, T. And we know that all of that equals some lambda 3 minus 4, because that V is in the direction 3 minus 4, so it's some factor of it. So we get minus 1 plus 2t equals 3 lambda, and 4 minus 3t, which is minus 4 lambda. And we solve those simultaneously, and we get t equals 8. We're now told at time t equals 4, p is at the point P. So we're finding a distance. So we're using S equals ut plus a half AT squared. So we've got S equals U, T, and do we know what T is? Yeah, we know it's 4, plus a half A, which we know is 2 minus 3, t squared, which is going to be times 16. And we work that out and we get 12.8. But that isn't our distance. That is the position vector. To find the distance is like finding the magnitude. We have to Pythagoras it. So the distance is going to be the square root of 12 squared plus 8 squared, which gives us 14.4222 something. So let's say 14.4 meters. Okay, next question. 7. Oh, this looks interesting. Let's have a look. Okay, so we've got a train on a horizontal train track. Moving at speed 16. Sorry, I'm reading it through with you guys. Okay, so essentially, we want to find the distance traveled, which is the area under the curve. However, there's a wrinkle in this. This is in minutes. This is in meters per second. So when we find the area, we're also going to have to times it by 60 to put it all into the correct units. So we've got two trapeziums. Remember, the area for trapezium is half the sum of the parallel sides. Sorry, I'm starting to sing. It goes to pop, goes the weasel. And half the sum of the parallel sides times the distance between them. Anyway, so I can't sing, so I probably should not even start. So we've got half a plus b times h. So let's take the areas of each of them, and remember we're going to times them by 60. So here we've got this length, which is 17. This has got 1 and 1 either side, so that's going to be 15 and 17. So this is going to be 15 plus 17 divided by 2 times 16 times 60. And this one is going from 21 to 33. So 33 minus 21, which is going to give us 12. And then this bit is 1 either side as well, which is 10. So a half, 10 plus 12 times 16 times 60. I'm going to add them both together to get the total distance traveled, which gives me 25920. That's going to be meters. Does it ask us for any particular units? No, but I'd probably change that to kilometers. If you didn't, it wouldn't matter. 24.92 kilometers. Okay, so hopefully that makes sense. So now we have a second train that leaves A at t minutes. Okay, fine. Afternoon. So it doesn't actually leave at 0, it leaves a little bit later. Let's draw it on its own speed time graph. So instead of leaving at 0, it leaves somewhere here. Okay. It moves in the same direction. It accelerates uniformly from rest for 2 minutes. So that's minutes if we use the same axes, until it reaches a speed of 24. And then it keeps going at that speed, and we don't really know how long for, so that's fine. So we know that they've traveled the same distance. Okay, so this length here, if you like, is going to be, oh, we've used t. Okay, let's choose a different letter. So this distance here, I'm going to call it, I don't know. Why can I not think of a letter right now? It honestly doesn't matter. We're going to call it A. Okay. So if this is A, then this bit here is A minus 2. Okay. And we're going to find the area of that. So the area of that is going to be a half A plus A minus 2 times by 24. And then because we're in minutes and we've got meters per second again, we've got to times that by 60. And all of that is the same distance as what we found up here. So we're going to make that equal to 25920. And you're going to solve that, nice simple algebra. And A comes out to be, she says, A comes out to be 19. So we end up with 19 here. So that equals 19. Right, what are we trying to find? So we're trying to find, scroll up a bit, the value of t, which is this number here. So we know the entire thing is 33 because we had that from the previous question. So 33 take away 19 means that this bit here has to be 14. So your answer will be 14. All right, let's scroll up. State one assumption that made in your working that could affect the accuracy. Well, the trains we assume are just particles, so they have no length, which it doesn't really make sense. The platforms, we haven't considered how long they are. Anything sensible, you know? Generally talking about the assumptions of length is usually a good one to do. Right, let's do the next question. Okay. Oh, here's a fun question. Is that the next one? Yeah. So a car moves along a straight horizontal road. The car starts from rest at a fixed point A and moves with constant acceleration for 30 seconds, reaching a speed of 15. When the car has been moving for 15 seconds, a motorbike starts. Okay, so we're drawing a speed time graph essentially. So we've got time and we've got velocity, and we've got time in seconds, be sensible here, and meters per second. Okay, so let's draw the car first. The car starts at 0 and it moves constantly for 30 seconds. So let's say it's 15 and there we go, 30. So it moves in a straight line like that, after which it just keeps going straight. Okay, perfect. So that's my car. When the car has been moving for 15 seconds, so the motorbike starts at 15, and it accelerates at 1.5 meters per second. So what I've got to think about is at this point, 15 seconds later, where this car, so I want to know how it crosses essentially. What speed will the motorbike be going at? So if it's moving at 1.5 meters every second, in 15 seconds, it'll be 1.5 times 15. So at this point here, it'll actually be bigger because it'll be 22.5. So it's going to have a line that goes, so this line here is going to go like that. And we don't know how far it keeps going up for. So then it might keep doing that because it just keeps accelerating. Okay. So when I draw it, and I can draw a line down there and a line down there. Okay. So now those are my axes. And when it catches up with the car, it means that their distances are the same. But I don't know what those distances are yet. So for the car, let's actually split this into so we can find out this distance here. So I'm going to call this distance here. I'm going to call this distance here T. Oh, let's put 50. So this distance here is going to be big T. So if I look at the car, I've got a triangle there, which is 30 times 15 divided by 2. So the car, the distance is 30 times 15 over 2 for the triangle, plus this rectangle, where this distance here is actually, let's call, sorry, I'm going to do this because it'll be easier to equate them. We're going to call this whole distance T. So until the point, so we're talking about until the point, the entire distance, which we're going to consider when they meet. So let me erase all of this and make this a lot clearer to see what I'm trying to show you. So we're finding this area. So we're going to call this bit T. So then for the car, you've got this triangle and this rectangle bit here, which is T minus 15, T minus 30 even, times by 15. So if I simplify that, I get 30 times 15 divided by 2 minus 30. So I get T, is that right? Yeah. So I get 15T minus 225. That's right, 30 times 15 divided by 2 minus 30 times 15. Yes, okay. Now for the motorbike, this is where it's a little bit trickier because I don't know what this height is. I do, however, know that this is 1.5. So I know this bit is 1.5. And I know that this distance here is t minus 15. So logically, if I know the gradient, so not this distance, sorry, this m, if you like, this gradient is. So my change in y, which is what I don't know, so let's say change in y divided by t minus 15 equals 1.5, then my change in y, so my height, has to be 1.5 multiplied by t minus 15. So that's the bit that makes this a little bit tricky. So we've got our motorbike, which I can see is a triangle. So half the base is t minus 15, times the height, which is 1.5 t minus 15. Now we're going to equate the two. So we're going to make this equal to this. And when you do that, and I'm not going to clean it all up, I'm going to let you do that, you'll get t squared minus 50t plus 525. And then when you plug it in your calculator, you get t equals 35. Right, so that's telling you this whole length is 35. It's asking for you the speed of the motorbike at the instant it catches up. So essentially, we're trying to find this height here, which we know is t minus 15 times by 1.5, because that's what we found over here. So it's going to be 1.5 multiplied by 35 minus 15, and we get 30 meters per second. So that is a little bit tricky. You need to picture it and think about it, but that's how that works. Assuming YouTube lets me, I'm going to continue with these until I sort of fall asleep, but let's see how far we get. So